Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Muhammad Tahir and you are watching my YouTube channel Engineering Studio. In this video we are going to solve one example related to development length of deformed bar in tension. So a 400 mm wide cantilever beam frames into the edge of a 400 mm thick wall. To reach the M0 nominal capacity of that beam, the three number 25 bars at the top of the beam are stressed to their yield strength at a point A, as shown in the next figure. To compute the minimum embedded length, embedment of the bar into the wall, and the development length in the beam. The concrete is low density concrete with the strength 25 megapascal. The yield strength of flexural reinforcement is 420 megapascal. Construction joint is located at the top and bottom of the beam. The beam has closed number 8 stirrups. So there are number 8 stirrups at the spacing of 180 millimeter having yield strength 420 megapascal. The cover to the stirrup is 40 millimeter. The three number 25 bars are inside the number 13 bar used as vertical steel of the wall. So let's see a figure in the next slide. So in the example it is explained that we have a wall. This one is wall and a beam is embedded inside this wall. And the construction sequence is like this. First the wall up to this length, this height is constructed, then this beam is constructed, and after that this wall beyond this is constructed. So at these two locations, before the start of beam and after the casting of beam, there is a construction break, so that's why there will become construction joints. The next information which is given is the bar at this point A will yield. So this beam is reinforced as a tension control member. So when it is designed as a tension control member, so at this critical location the bar will yield. So it has three number 25 bars at the top. The height of the beam is overall height is 450 millimeter and the effective height is 387.5 millimeter, and the projection of the span of this cantilever beam is 2 meter. The width of beam is 400 millimeter, equal to the width of this wall, and this wall has number 13 bars at the rate of 300 millimeter, and the clear cover to this wall is also 40 millimeter, and the clear cover to the stirrups in the beam is also 40 millimeter. And these bars, these number 3 bars, are located inside these vertical bars. So these are the information given in the example. And for transverse reinforcement, the information given is that they are number 10 bars at the rate of 180 millimeter with Fy 420. So what we are required to do in this case, we need to calculate this development length. The development length from the face of the wall to the inward direction, so that need to be provided for the development of this bar to get the yield strength at this point A. Similarly, we need to find the development length inside the beam. To embed this bar inside the beam, we need to calculate this development length. How much length should be projected or embedded beyond this A point inside the beam. So these two informations are required. So actually in both the cases we need to calculate the development length for this case as well as the development length for this case. So here in the case of wall, there is no transverse reinforcement, no stirrups, and in case of this beam there will be stirrups. So because of these two different scenarios, the selection of the equation for development length will be different. Okay, let's solve this example. First of all, the development of bar in the wall. So to calculate the development of bar in the wall, to calculate the LD, first of all we need to check the case. If we want to use the detailed equation, then no need to check for the cases. We can directly use that equation. And if we want to use the approximate equation given in the table 25.4.2.2, in that case we need to first check the case. Which case is this? And corresponding to the case, the size and spacing of the bar, we need to select the equation for development length. So first we will do it with the approximate equation. So to select the approximate equation, first need to check the spacing and cover. So the cover up to these bars is equal to, here the cover is 40 millimeter and the bar is 13, and then there is a steel bar. So 40 millimeter plus 13. So this will be the cover up to these bars. So the cover for the 25 bar is 40 plus 13 millimeter, and this is equal to 2.1 time diameter of bar. Similarly, the spacing between the bars, the spacing between these two bars. So we can calculate it. We need to subtract the cover up to this bar on this side, and the cover on this side, and then the diameter of the bar. So from overall width 400, if we subtract the cover on both the side and we subtract the diameter of the bars for all these three bars, then we will left with these two spaces, and we will divide it by 2 to get the clear spacing between the bars, so which is 110 millimeter, and it is equal to 4.4 time diameter of bar. I mean 110 divided by 25 millimeter, it is equal to 4.4. So it means the spacing between the bars is 4.4 times the diameter of bar. So as the clear spacing between the bar is more than 2 times of the diameter of bar, as well as the clear cover is greater than the diameter of bar, so as there is no transverse reinforcement, so this case will not be applied. So we can only check this case, and for that case the spacing between the bar should be more than 2 times the diameter of bar, but in our case it is 4.4 times. And for the clear cover, it should be more than diameter of bar, but we have 2.1 times the diameter of bar. It means these two conditions are satisfied for this beam inside the wall. So this case 2 will prevail, and we will select the equation corresponding to this case. I have placed the table here along this slide. So here we can see this case is prevailed, and the diameter of the bar is more than 22 millimeter, which is 25 millimeter actually. So we will use this equation to calculate the development length. So our selected equation for development length is this one. LD is equal to Fy psi t psi e over 1.7 times lambda times the square root of Fc prime diameter of bar. So now we have selected the equation for development length. Now we need to select these parameters. So first of all, psi t, which is a location factor. So in this figure we can see that the position of these bars is at 387.5 millimeter from the bottom. So as this 387 is greater than 300 millimeter, when the location of this bar is above the 300 millimeter, so it means we need to consider this psi t factor. So we can consider this site factor from the table. So I have placed the table over here. So for site, more than 300 millimeter of fresh concrete placed below horizontal reinforcement. So in that case, its value is 1.3. So I have selected this value 1.3. The next factor is psi e, epoxy coated. As in our case, the bars are not epoxy coated, so its value will be 1. The next is lambda. So in our case, the concrete is low weight concrete, lightweight concrete. So lambda will be 0.75. So now we have these three factors, psi t, psi e and lambda. Now we can calculate the development length. So development length will be equal to, here this factor 1.7, we can also write it 12 by 20. So these two are equal. 1.7 is equal to 12 by 20. So here 12 by 20. So this is actually factor 1.7 times Fy 420, psi t 1.3, psi e 1, lambda 0.75, Fc prime 25, and the diameter of bar 25. When we will solve this equation, so the answer will be 2180 millimeter, 2.18 millimeter. So what it means, we need to extend this bar 2.18 meter into the wall to develop the full yield strength. So extend the bar 2.2 meter into the wall. So this length will be equal to 2.2 meter. So this was our first question that we need to answer, how much will be the development length inside the wall. The next is to calculate the development length for this beam. Okay, development length of bar in the beam. So for that, compute the development length for number 25 bar in beam using equation from the table. So again we will use the approximate equation. We will select the equation from the table. So to select the equation, suitable equation from the table, we need to select the case. We need to check the spacing between the bars, clear cover, and the transverse reinforcement. So the first, clear spacing between the bars, it should be more than 2 times diameter of bar. So it is okay, because we have calculated in the previous case the spacing between the bar is more than 2 times diameter, which was 4.4 times diameter, so which is more than 2 times diameter of bar. The second was the clear cover to the bar should be more than diameter, and in our case it is 2.1 times. So both these conditions are satisfied. The stirrup fulfill the minimum requirement of ACI 318 section 9.6.3.3. So this condition need to be checked. So to check this condition, these two conditions should be fulfilled. Spacing of the stirrups, it should be less than d by 2. The effective depth of the beam divided by 2. So in our case the value is 180 and the depth is, effective depth is 387.5. So half of it is more than this 180 value. So it means this is also satisfied. And the second thing that we need to check is area of steel provided, transverse steel, should be more than area of steel minimum. The minimum area of transverse steel can be calculated by using these two equations which are given in ACI code. So when we will use this Fc prime 25 megapascal inside this equation, where BW is the width of this beam, S is the spacing 180 millimeter of the transverse reinforcement, Fy is the yield stress of the transverse reinforcement. When we will substitute these values, so minimum area of the transverse reinforcement comes to be 60 millimeter square. But in our case, we have 2 leg stirrup like this. So the area of these 2 leg is 2 times the area of single leg. The area of single leg is 75 millimeter. The area of number 10 bar is 75 millimeter. So in our case, the area provided is 142 millimeter square, so which is greater than this 60 millimeter minimum transverse reinforcement area. So the case 1 will prevail. As we have seen in the previous case, from the table the first row will be used and the equation of the second row will be used. We can see now this condition is satisfied. So once this condition is satisfied, we will use equation out of these two, and the diameter of the bar is 25 millimeters, so this equation will be used, and this is similar to the previous case. So as this equation is similar to the previous case for bars in the wall, so it means the development length calculated by this equation will also be the same. So the development length calculated will be again 2.18 millimeter, sorry 2.18 meter. And in our case, the span of the cantilever beam is 2 meter, but our required development length is 2.18 meter. So it means we cannot develop this bar inside this concrete. So either we need to extend the beam, which is not possible. The second case is either we need to reduce the diameter of this bar to reduce the development length of this bar so that we can develop inside this concrete portion. Or the third thing is we can check this development length by using the detailed equation, and if the required development length comes out to be less than this 2 meter, so it means okay, we can develop this bar within this beam. Otherwise we will left with the one option to reduce the diameter of bar. So let's check if we use the detailed equation, can we develop this bar inside this beam or not. Okay, the detailed equation is this one. Here Fy, Fc prime, C, psi t, psi e. We are familiar with these factors. So the only new factor is psi s, which is for the size, and for 25 millimeter bar its value is 1. And the next factor is psi b, which is actually smaller of this cover or the spacing between these two bar, 1/2 of the spacing. So the clear cover in this case is, we have already seen for the longitudinal bar 40 millimeter cover plus 10 millimeter diameter of stirrups plus half of the diameter of this bar. So this will be our clear cover, so which comes out to be 62.5 millimeter. And for the spacing of the bars, we have already calculated, or we can again calculate. 400 is the total width, and 2 times this cover, cover on one side. Similarly, as we have 3 bars, as we have 3 bars, so this cover as well as this cover, so both are same 62 millimeter. So 62 millimeter, 62.5 millimeter times 2, so we need to subtract it from 400 millimeter, and when we will divide it by 2, we will get center to center spacing of the bar. Here we have not subtracted the diameter of this bar. Why? Because we want center to center spacing inside instead of clear spacing. So it comes out to be 69 millimeter. So the smaller out of these two, 62 millimeter and 69 millimeter, will be considered as CB. And the next factor is KTR, which is a factor for transverse reinforcement. So KTR is given by 40 times area of transverse reinforcement divided by spacing of transverse reinforcement multiplied by the number of bars. So 40 times area of bar is 2 bars, we have 2 leg stirrup, and the area of one leg is 71, and the spacing is 180 millimeter, and number of bar being developed are 3 number 25 bars. So 3 bars are being developed. So n is 3. So when we will solve this, KTR will become 10.5. 40 times 142, 180 times 3. So now we can calculate this factor CB plus KTR over diameter of bar. And this factor is termed as confinement factor. So this factor comes out to be 2.92, and which is more than 2.5. So we have seen that there is a limitation on this confining factor. It should not be more than 2.5. So we will select it equal to 2.5. So now we have all these parameters for this equation for development length. We have all the parameters. So now we need to substitute these parameters in this equation to get the development length. So when we substitute these values, Fy, lambda, Fc prime, psi t, psi e, psi s, and the confinement factor. So the value come out to be 1320 millimeter. Now it is the required development length, and the available length of the beam with us is 2 meter or 2000 millimeter, and this 1320 millimeter, 1320 millimeter is less than this 2000 millimeter. So it means we can develop this bar inside this beam. And we can also observe here that the value calculated by this exact equation, which is 1320, is significantly less than the value 2180, which was calculated by using approximate equation. So approximate equation highly overestimate the result. They go into the conservative side, but if we want to calculate the exact value, so this detailed equation can be used. So it is less conservative. Thank you very much. This is all for this video. In the next video, we will discuss about the development length of standard hook in tension.